Hello viewers and welcome to a new STM32 World tutorial video. In this video, as the video on the screen should indicate, we will be looking at RGB LEDs. The video is going to be slightly unusual compared with my other videos in that I am not going to develop a library for this from scratch, but I'm going to use one I developed a couple of years ago. It would simply take too long, but I'm going to try to explain all the details as we move along, so hang along until the end of this video and you will know how to use these RGB LEDs for yourself. Okay, let's look at RGB LEDs. If you Google for RGB LEDs, you will find that a typical RGB LEDs is either a common anode or common cathode, and then you have one, so they will have 4 pins, and you will have 1 pin per color, and then you will have a common either going to ground or the power comes in from the common. I think the common anode is probably the most common, but I'm actually not sure about that. But it's pretty clear that if you want to drive one of these from an STM32, you will either need a GPIO expander or you will need to allocate 3 GPIOs for each and every LED. And if you want to actually control the color, you need to run PWM. We've seen in earlier videos, go back and watch those, how you can drive the intensity of a LED by using pulse width modulation, PWM. It's pretty clear you would dedicate 3 timer channels to run one of these RGB LEDs. Fortunately, there is an alternative to this, and that is called WS2812. These are known as NeoPixel, or they are known as addressable LEDs, and the idea is that you send them a bit stream for each of the 3 colors. No, you will send them 1 bit stream, but that bit stream will contain the intensity of each of the colors, and then the device itself will run the actual LEDs. You can Google and YouTube, there are plenty of examples of this. These NeoPixel devices are really quite cheap. If we look at AliExpress and search for WS2812, don't do that, 2812, you will see that there are plenty of strings with these. There are circular, if we look at this, you can get them in rings, you can get them in panels, and well, there are a lot of options, and they are really, really cheap. In this video, we will be using one of these panels, which contains 64 of these RGB LEDs that can be addressed, and you can see here on AliExpress they cost about $1.50 for 64 LEDs. It's amazingly cheap. They are cheap and they are very reliable, and once you figure out how to run them, they are not that hard to use, so comes highly recommended. Now, this I have created, of course, as I always do, a page on the STM32 World Wiki where you can read more up about this. The interesting part about the WS2812 is the protocol with which it is driven. Now, the way they are wired up on a PCB is that it is a long string of LEDs, and each of these LEDs will have a data input, and then it'll go data output into the next input, and so on and so forth. And you can actually drive, I think, up to about 1,000. We can get back to a calculation for that later. It's timing. You run out of timing if you make them too long. But you can run quite a lot of them. So the protocol is, there's no clock going through this, so it's an asynchronous you need to keep the timing right. We'll get back to that as well. But if we look at this, you'll see that you send data to these, and 24-bit will be used by each of the devices. So once this device, you'll send 24-bit to indicate the RGB values, and then when there are more bits, that will be sent to the next device in the chain. So it'll look like this. You'll send the first 24 bits, and then second LED will take the next 24 bits, next LED will take the next 24 bits, and so on and so forth. So you can see if there's 1,000 LEDs, that is quite a lot of bits that needs to be transferred. One thing that is important to notice here is that they, for some bizarre reason, do not come in order. These take green first, and then red, and then blue values. Now, the actual data that you're sending consists of a 0 or 1 and nothing else. There's also a reset, but that is simply zeros all the time. So if we look at this, we have a high value and a low value, a high value and a low value. And for it to be interpreted as a 0, the pulse width, the high, will need to be between 220 nanoseconds to 380 nanoseconds, within that range somehow. And in order to be the low part of a 0, it will need to be between 580 nanoseconds to 1 microsecond. High, on the other hand, is exactly the opposite. So you will have a high voltage time about a 1 microsecond. So roughly, very roughly, it's about a third. So if we have the entire pulse going this width, about a third and 2/3 here, and the other way for a 1. Now, if we do the calculation of this, we will see that they are running at a frequency of about 800 kilohertz. That is 800,000 bits per second. So each bit will take about 1.25 microseconds. If we look in here, we say if we take a 1, you have 1 microsecond here, and you have, where is it? I think there's a mistake here, but if we look at this one, you see about 250 here, and here we have 1 microsecond. So it works. If we send them at 800 kilohertz, and that is important, and then we do about a third high or a third low, that will work. Now, it's pretty obvious that at 800,000 bits per second and sending 24 bits would require quite a lot of timing if we were to bit bang this out on the it is certainly possible. I have seen it implemented, but it will take almost all of the MCU's CPU cycles to do this, and involve a couple of timers that would need to be controlled very precisely. So we need to look at an alternative. How do we do this without bit banging? Again, I have seen different implementations, but they all evolve around 2. We can actually use one of the SPI peripherals. And SPI, if you look at them one way, will consist of a clock and a MOSI signal. Now, master out, slave in signal. If we ignore the clock completely and just throw bits out on the bytes out on the MOSI, then we can actually imagine that we could achieve something like this. For example, if we send 111.0.0.0.0.0 versus 0.0.0.0.0.111, we would achieve almost what we are looking at here. A benefit of using SPI is that that could also be coupled with DMA. That means we could just fill a buffer of the data and then send it out. An alternative to this, and the approach that we will be looking at today, is using pulse width modulation. Now, we have looked at that in earlier video. I will strongly encourage you to go back and look at that video. I'll link them below. But if you look at those videos, you can see that a pulse width modulation on a timer, essentially you set a frequency that this runs with, and then you can adjust the duty cycle between them. So we will be looking at a frequency of 800 kilohertz with a duty cycle of about a third or slightly less than a third, and a duty cycle of 2/3 or slightly more than 2/3. And again, we will need to change that every single cycle, and again, that would require a lot of interrupts and a lot of callbacks unless we couple this with DMA. So we can actually fill these data into a DMA buffer, and then the peripheral will take care of sending these out one at a time. Now, for the project today, I am actually not using the regular STM32 fun repository that I put most of these examples in, because I have a library, standalone library. It's on my personal account, so LB Thompson /STM32-WS2812. You can go and look at it there. And there's a couple of examples as well, and it is reasonably well documented with screenshots how to get this up and running. So have a look at it there. But let's go in and look at the actual project. First of all, today, as you can see, let me show you that again. We're actually using a black pill board, STM32 F411, not our usual F405 base board, but it really doesn't matter which one you're using. It can be implemented on all of them. So let's look at the CPU setup, how this is configured. Well, essentially, first of all, whenever we're using a timer, it is absolutely essential that you know which clock frequency your MCU is running at. And if we look at here, the black pill board is running on a 25 megahertz crystal, which is being divided or multiplied actually up, so we end up with a MCU clock of 100 megahertz. Now, that value doesn't really matter for the timer calculation. What matters is over here, the APB1 and APB2 timer clocks, and you can see in this case, they are the same, and they're both running at exactly 100 megahertz. Now, let's, did I have a calculator somewhere? No, I don't. So let me fire one up, just to understand which timings are necessary. So if we take, oh, I had it. Oh, wait. Wait a second. I had a problem here. It was already running, so let me fire up a new one here. So if we take our frequency, which was 100 megahertz, and we divide that by 800 kilohertz, which is what we want, we will see that we end up with 125 cycles per, so 125 clock cycles per pulse to divide this down. Keep that in mind, 125. So let's look at the configuration. We have the usual stuff here. We have our the debug ports, we have a serial communication, we have our clock, we have the LED running, but most importantly down here is we have timer 4. So timer 4 will run on the internal clock. Don't know why I didn't actually check that. And then we will define a user constant. Here we have set one we call LED underscore CNT of 125, and then the setup of the timer is really simple. We don't have a prescaler, we run it full speed, but we will have an auto period of 100 the LED count, which is 125, and then we will run a PWM channel. So our panel is hooked up to PB6, and if we look at the device here, so it's hooked up to PB6 on this whole string is hooked up to that. So there you go. This is the basic configuration. There is one more thing that needs to be configured in here, is our DMA. So we need a DMA channel. So that will be timer 4 channel 1, which is a DMA stream memory to peripheral. So we have this DMA configured as a circular buffer, which here we go. So it will basically send half words to the peripheral, to the timer, and it will require half word. That is 16-bit values. That is important to remember. So without further ado, let's generate the codes as we always do. There you go, and we now have a main. Now, I have created a library called WS2812, and that is included in this subfolder. Source format. So let's look at the WS2812. If you look down here, we don't set up anything in this. We just call the WS2812 init, and we give it the timer, we give it the channel, and we give it the number of LEDs, and we have a handler. If you go back to my I2C video on creating a library, you will see in that video how to create a library handler for this. So let's look at the header file for our library. You'll see we have set a buffer size. Now the buffer size is basically, we need 24 bits per LED, right? And we basically have a buffer of those 24 bits. Now our actual buffer size will be double this size because of the way that the callbacks work when you're using DMA. You would get a callback interrupt when the buffer is half used, and you will get a callback interrupt when the buffer is fully used. So we will allocate double this. We will create some defines here. We have LED off. What indicates a LED off? That is our LED count, the 125, multiplied by 1, so 125, divided by 3, so that is a third of that, minus 1, so a bit less than a third. And LED on, we will say 2 times a third of the LED count and add 2, so a little more than 2/3. And we have a reset cycles. We need 10 of those between each string to indicate that we are starting all over again. We have the order of the values, so we have green first, and then red, and then blue. That's why these are orders 0, 1, 2. We have some enumerations. We have a result back from these things, and we have a state type def here. Now, the way to run this in the callback is like a state machine. So we have 3 states. We have the reset cycle, which we'll start with, and I don't think I actually explained this, so let's go back and look at this. So basically what happens here is, if we look at this data stream, the first 24-bit, as I explained earlier, will be taken by the first LED, and second LED, third LED, fourth LED, and then a reset cycle will indicate to this LED string that we are going back to D1. So between each, depending on the length of this LED string, there will need to be a reset cycle, which is quite long. Remember, these are running at 1.25 microseconds. So we are looking at a lot of these, but you can't make it too long. So we are just saying, okay, we go to 10 cycles. So that will be about 240 microseconds, right? Roughly. So that's it. Our handler will store the timer. No, sorry, I was talking about the state machine. So basically, we sent this reset, which is basically zeros, all zeros, and then we will go into an idle cycle where we are waiting for new data for the LED display, and once there is new data for the LED display, we start sending this data out, which is the last one. Once it is done sending the data, it will go back to a reset cycle. So our callback, our state machine, will cycle through these values again and again and again and again. Now, our handler, we store the timer and the channel. We create a DMA buffer. The DMA buffer is a fixed size of the 24-bit times 2. We will have the number of LEDs stores on the strings. We will have a dynamically allocated, we'll get back to that, buffer of all the values of all these LEDs. So that needs to be allocated. We keep track of the state machine. We keep track of, we have some counters down here, and we have this flag, which is important, is dirty. So every time we update a LED, we set that flag, and that indicates to our state machine to move out of idle and into our data transmission. We also have a couple of statistical counters down here where we keep track of how many times these are being executed. We'll get back to that. In essence, we have an init function where we pass this. That is the one we called in here in our main. And then we have some functions, some public function. We have one 0 LED values where we just basically blank the display. It is important, let me show you here, if we look at the device again, these LEDs, as long as they are powered, they will keep the value. So you don't need to refresh them. They just keep the color they are set at. So in order to blank the display, we will need a function for that. So 0 LED values will basically 0 all the values. And then we can set a LED value. We can set a LED with RGB. So we have, we can basically set the entire, for each color. So we can say red at this value, green at this value. We can also set all of them in one go, which we have here. So we can have a LED and then RGB, pass RGB to this. So that is the header file. That's all we have. No, there is one more thing, and that is we have our update buffer. Now, the library in itself is not handling the callbacks. That we do in our main. So if we look down here, we have our pulse finished half callback, and we have our pulse finished callback, and that WS2812 update buffer. So from our main, we'll call these buffers. This is the only way actually to have that handler transferred, because when the interrupt happens, we don't know which, there could be more than one. So we handle this in the main loop where we have the WS2812 handler, and then we send that to the update buffer. Let's look at the library itself. No, there's one more thing I want to say. Now, it is pretty clear that these bits that are sent, which is like high, low, high, low, high, low, they need to be calculated for each specific color. And to have as little overhead as possible, I am actually doing a color value array in here, so we can simply look up in that area. If we go back to our header file, up in the beginning, we created this LED on, LED off, LED on, which is basically a value, 8-bit value. So in here, we create this color value table, and it is 256 8-bit values. So we have for 256 each color, we have 8 bits. So we have LED off, 8 of those, and then 1, 2, 3, etc. up to on all the way. So this is, I use this lookup table to do it faster. It could easily be calculated, but it will take longer to calculate these values than simply looking them up in a lookup table. As I mentioned here, we waste about 4 kilobyte of flash on this, but I mean, we got quite a lot of flash, so I'm not too worried about that. So let's look at the C library, what we have here. So we basically have this, let's look at the initialization first. Down here, we pass the handler, timer, all the other things. So the first thing we do is to store these values in our handler. We set the is dirty to 0 because it's not dirty as this time, 0 halves. We set that to 2, and then we allocate the memory for enough of the number of LEDs times 3, because we need 3 bytes per LED in this chain. Then we set all this to 0, so it will start up with a blank display. We start the timer PWM with DMA and pass it the buffer, and at that point it is running and we get the callbacks. Now if we look at the functions down here, the 0 LED values is basically set everything to 0 with a memset. Make sure to make the buffer dirty, because we need, if it's blank, we need it to be updated blank. Set LED values, I simply update the array that we allocated down here. We treat that as a value. So we basically have a couple of methods of doing this, and that is it. These methods are really, really simple. The meat of this library is this callback. Remember from here that this is callback for every 24 bits that are being transferred out to the LED string. So each LED 24 bits RGB values or reset will be sent out, and this will be called, and we will have a pointer, which is the second variable, second parameter. So this will actually point at the next one that needs to be sent out, and we have the handler and we have that pointer to this buffer. So if we look in here again, you'll see when the pulse is half finished, we update the beginning of the buffer. When the pulse is finished, we update the second half of the buffer, because then it will be sending the first half. So it is toggling between those two. So if we look at this callback itself, I'm probably not going to go into understand it fully, but I'll explain it in detail. First of all, we update this DMA callbacks. We use that for statistics. I want to know how many times this function has been called. Then we get down to our state machine, which can basically be reset, it can be idle, or it can be else. It is let dead, where we're actually updating the data of this. So if we start with the reset, this one is very simple, right? We have a bunch of zeros of the right size, we just throw that into the buffer, right? And we need to send twice of them because we want to go through 2 half buffers, go through this. So we basically fill the DMA buffer with zeros, and we update that 0 halves count so we can keep track of them. And then when we have finished this exercise and send out 2 of these, we switch the state machine If it's not dirty, if it's dirty, we go into data sending. If it is not dirty, we will go into idle. Now, idle is the next state. We basically don't do anything except check for the dirty flag. And if it's not dirty, we'll just wait there. If it gets dirty, that means that we have updated one of the values down here where we set the is dirty flag. If it is dirty, it will actually move into the data transfer. It will set dirty false again, and then it will go into start processing the data. So down here we have another statistic counter that we keep track of, which is our data callbacks. That should be lower than the total callbacks, so indicating that we are spending time in the other states of the state machine. Now, if we look at the LED data, first, let's deal with the current LED. So whatever LED we are actually handling, we create a pointer to the LED we're handling right now, which is in our LED array for each LED. So we have the value of the LED in this pointer. This points to the value of the current LED that we're talking about. And then we go to the three colors, RGB, deal with each color of that LED, and for each of those, we look up in our color value symbol, and we basically transfer. Remember, this is actually from in here. If we look at the DMA, you will see that it's actually using half words. So it will use 16-bit, even though we are only using 8-bit, but we are basically looking up the color value table. I think that is defined as, color values. It is UN16, so we are actually indicating 16 bits, even though we are only setting 8 bits. That's fine for that. So we are copying from the color value table into our current DMA buffer pointer, and then we move on to the next 8 bytes, since we're actually using 8 bits for 1 byte, so it is a little bit complicated. Then we move on to the next LED by switching the reset. No, we are handling that, and then we are moving on to the next LED, or to reset when all the LEDs have been updated. So we are basically updating our LED count to the next LED. If we have reached the number of LEDs, we basically go back to a reset pulse. If not, we'll wait for the next time this update buffer is called, and we'll be handling the next LED, and so on and so forth. It looks a little bit complicated, but once you realize how it's working, it is actually quite simple. So let's try to run this, and let's look at the I have hang on a second. I need to I have one running somewhere else. Let me kill that. There you go. Oh, let's try to run again. So we can see we user one, we basically check every second, and we'll see we count the idle loop and how many DMA callbacks did we get and how many data transfer did we get, and that is about it. Now, in order to use this for anything, I have created demos here, and at the moment it is really simple. It basically sets some colors, R, G, B, and then yellow, cyan, and green, I think, blue, I think it is, and and basically I call a demo tick where we basically use the 0 LED values, we blank the display, and we send out new ones, and this essentially look like this. Now we could, for fun, try to not zero it and run it, in which case it will just start lighting up and changing the color because we are not blanking it. So there are multiple ways this can be run. It is, of course, just called from our main loop, the tick. We divide by 10 here, so it's only called every 10th time. This, our demo loop, is only called every 10 times, so that is about it. Now, I would encourage you, if you're actually trying this library, to come up with some more impressive demos. I have created, you can set different demos, so it would be entirely possible down here to have switch active demo. It could have 2, 3, 4, 5, 6 different demos that look different, and as usual I forgot to switch that off. So I would encourage everybody that is actually trying this library to come up with some impressive demos, and if you do, please submit a change request to the Git repository or just send me a message somewhere, and I might include it in this library for people to use in the future. So that is about all I wanted to say today. It sounds complicated, and it is complicated, but once you get the method of this, you can see that the code here is actually really simple. Now, I'm always, as you can see from my earlier video, I'm always questioning myself, and one of the things I dislike about this library at the moment, I don't like this value table here, and I would be open to if this could be calculated on the fly faster than looking it up, or almost just as fast. I would be open to ideas. One of the ideas that I am considering, which I think might work, is rather than calculating this, actually using the bit banding features. The reason I think I didn't do it in this library is that not all STM32s have a bit banding feature enabled. The earlier ones have, but the later dual core, etc., they simply ran out of addresses to do that recently. So I think they did that feature in some of the newer MCUs, but it could potentially be done without bit banding. So we're talking about this line here where I put these values into the DMA buffer pointer. Yeah, and if there is an easier way to do that, that would be very, or not easier, but faster way, or just as fast. So I don't particularly like doing these lookup tables, but it seemed the best way of dealing with it in this particular case. So there you are, viewers. That is pretty much all she wrote. I hope that you gained a reasonable understanding on how these RGB LED strings can be handled. And I hope you enjoyed this video and stuck around to the end. I always love comments below, so please do comment, good or bad. I am still learning to do these videos, so I'm trying to get better, and the only way you can get better is to listen to criticism. I am my own worst criticizer, so but I always appreciate anything else. So please do let me know below what you think about this video and whether you enjoyed it or whether you used this library. Thank you very much and enjoy the rest of your day.